So, in today's lecture, we're going to talk about the equation that describes the damped harmonic oscillator. Now, we've covered harmonic oscillators before, okay, a lot, but we've always assumed that everything was perfect and that there was no friction or drag. We pretended it didn't exist, but of course in real life it does exist. So how are we going to model that mathematically, and what are we going to do? So let's consider friction, and let's specifically consider viscous friction because we have a nice solution for that one. And then it turns out that this model of friction actually works pretty well for describing a lot of systems. Now what we're going to focus on today is underdamping, which is something that oscillates for a little bit before it stops. But we'll touch briefly on critical damping and overdamping, really briefly, and I'll then leave that to your upper level professors. But I'm getting ahead of myself. Let's go ahead and talk about the damped harmonic oscillator and how we're going to model it. Okay, so let's think about what's going on here. Let's look at our free body diagram and consider what the forces are acting on our mass on a spring. Okay? So what we've got here are two forces now in the horizontal direction. We're going to let it oscillate in the horizontal direction, okay, so that we don't have to worry about gravity. And we're going to say that we have the two forces of Hooke's law, the spring force, which is a restoring force that always pushes the object back towards the equilibrium point. And then we have viscous friction or damping, okay? Now, the equations for that are Hooke's law for the spring force, F is equal to minus kx, right? And remember, k here is the spring constant. And if you put your origin at the equilibrium position, then x is the displacement of the mass from equilibrium. And then we have that force, and then we have the viscous friction, which is minus CV. C is the damping coefficient, and V is the velocity. So the frictional force has a minus sign in it because it's always opposing the direction of motion. Okay? Now we're focusing here on 1D, the equation in one dimension. And so if we sum our forces up, that's minus kx minus cv, and then we set that equal to F equals ma via Newton's second law. Okay, so we have ma is equal to minus kx minus cv. Now, a is the acceleration, which is the second order time derivative of the position, md squared x dt squared. And then that's equal to minus kx minus c dx dt, because v is the first order time derivative of the position. All right, now, what we do to solve differential equations, first off, is to guess and check, okay? So that's definitely one valid way to solve differential equations. So what you do is you figure out kind of what's going on, and then you make an educated guess as to what the solution is. And then you plug that solution into your differential equation, and you see if it works. And if it does, eureka, you've solved it, right? So that's the guess and check method. So we need to make an educated guess, though. Just any old stupid guess won't work. So let's talk about what's happening. All right, so if you have a simple harmonic oscillator with no damping, we've already solved that one. And we know that that one is a sinusoidal function. So we described it specifically by the position as a function of time is equal to a times the cosine of omega naught t plus phi, right? Okay, now omega naught is what I'm going to call the undamped frequency of a simple harmonic oscillator from now on. And that's the one that you're already familiar with. Omega naught is equal to the square root of k over m. Okay, so it's the square root of the spring constant k divided by the mass attached to the spring. And then, of course, phi is the phase constant. It's just an offset where you start your clock at t is equal to 0. Okay, so that's our solution with no damping. Now, if we think about what happens when we allow friction or damping on an actual harmonic oscillator, what we usually picture in our head is something that starts to oscillate, and then the amplitude of the oscillation gets smaller and smaller until it eventually comes to a stop. Okay? Now, if the amplitude is decaying over time, that sounds like a decaying exponential to me. So a good guess for what's happening to the amplitude might be the initial amplitude A times e to the minus alpha t. Now, alpha here is just some undetermined constant. I'm not saying what it is, I'm just saying it's some constant value. Okay, we're going to solve for it later. And then it might be a good guess just to take what we had for our sinusoidal function before and plug that in. And so now we have a e to the minus alpha t times cosine of omega t plus phi. Now, I am not saying here that I think that my frequency of oscillation, right, is going to be the same as for the undamped case. That's why I changed my notation for omega naught being the square root of k over m, that's no damping, no friction, versus now I'm calling it omega. So I don't know what omega is, and I don't know what alpha is. So those are my two undetermined constants here, all right? And I would solve for them as I go along, okay? So that's my guess. That's my educated guess. The amplitude is going to decay exponentially, and it's going to wiggle back and forth while it does so. All right, so now comes the hard part, which you have to do once you've made your educated guess, is to plug it back into the equation and see if it works, okay? So that means that we have to take some derivatives of our function. So specifically, we have to take the first order derivative, and then we have to take the second order derivative. So let's try that, and then plug those derivatives in and see what we get. So we're going to use the product rule a lot today. Remember that if you're multiplying two functions and you're trying to take the derivative of those two multiplied functions, you do the derivative of the first times the second plus the first times the derivative of the second. That's your product rule. So that's what we've got here. We've got that decaying exponential times the sinusoidal function. So we're going to first take the derivative of the decaying exponential when we do our dx dt, and that is really easy to do, right? We're just going to have minus alpha times a e to the minus alpha t, and then I leave the cosine alone, times cosine omega t plus phi. Now I'm going to leave the exponent alone, the exponential alone. I'm going to take the derivative of the cosine. So if I take the derivative of cosine omega t plus phi, I get minus omega sine omega t plus phi. So for my second term, I have minus omega a e to the minus alpha t sine omega t plus phi. Now if you need a minute on that math, or if you need a moment on the math at any time during the video, just remember you can pause me and think it through and then restart, okay? So now I'm going to rearrange some terms, make it a little easier to look at and deal with, and I'm going to pull the a e to the minus alpha t out, okay? And everything's negative, so I'm going to pull a minus sign out too. So I've got dx dt is equal to minus a e to the minus alpha t, now times, right, alpha cosine omega t plus phi plus omega sine omega t plus phi. All right, now I need to take the derivative of dx dt so that I can get my second order derivative of x with respect to time. So I have d squared x dt squared, and now I've got the product rule that I have to apply on dx dt. So for my first function, I have this minus a e to the minus alpha t, and then for my second function, I have the stuff in the curly brackets here, alpha cosine omega t plus phi plus omega sine omega t plus phi. All right. So taking the derivative of the decaying exponential first, I'm going to have minus alpha times minus a e to the minus alpha t, which gives me a alpha e to the minus alpha t, and then times the stuff inside the curly brackets, leaving it alone. Alpha times cosine omega t plus phi plus omega sine omega t plus phi. Now I'm going to leave the decaying exponential out front alone and take the derivative of the stuff inside the curly brackets. So that's minus a e to the minus alpha t times. Now remember, the derivative of the cosine is the sine, minus sine, and the derivative of the sine is the cosine. So here we go, minus alpha omega sine omega t plus phi plus omega squared cosine omega t plus phi. All right, so that's my second order derivative of the position with respect to time. Now I have to take those derivatives that I just took and plug them into my full differential equation. So rearranging my differential equation so that I don't have anything pesky multiplied times my acceleration, I get d squared x dt squared is equal to minus k over m x minus c over m dx dt. Okay? Now we're going to plug and chug. We're going to plug it in. We're going to take this d squared x dt squared, that becomes my left-hand side. Okay, so that's a alpha e to the minus alpha t times alpha cosine omega t plus phi plus omega sine omega t plus phi minus a e to the minus alpha t times minus alpha omega sine omega t plus phi plus omega squared cosine omega t plus phi. Now that's my left-hand side. And it's equal to the right-hand side, which would be minus k over m times x. Now remember, our original guess for x was a e to the minus alpha t cosine omega t plus phi. So I have minus k over m times that. And then I have minus c over m times dx dt, which I solved for up above. So I have minus c over m times dx dt, which is minus a e to the minus alpha t times alpha cosine omega t plus phi plus omega sine omega t plus phi. So really I'm just plugging and chugging here. Okay. Now I need to simplify and figure out what the heck is going on with all this stuff. So taking everything that I had at the bottom of the last slide and putting it at the top, let's now see if we can simplify this sucker a little bit. Notice that a e to the minus alpha t is in all those terms. And if something is in every single term, you can just cancel it out. And that'd make things a lot simpler, wouldn't it? So if I do that, if I cancel out my a e to the minus alpha t, then I'm going to have a much simplified left-hand side. I'm going to have alpha squared cosine omega t plus phi plus omega alpha sine omega t plus phi plus another omega alpha sine omega t plus phi minus omega squared cosine omega t plus phi. Now what I'm going to do on both of these sides, but I'll do the left-hand side first, is I'm going to group like terms. So what that means is I'm going to take all the cosines and put them together, and I'm going to take all the sines and put them together. I'm going to do that on both the left-hand side and the right-hand side. So left-hand side first, which I just expounded on, let's go ahead and factor those things out. So I have alpha squared minus omega squared times cosine omega t plus phi, and then plus 2 alpha omega sine omega t plus phi. And that's my left-hand side, which was originally my d squared x dt squared side, right? Okay, now let's look at the new right-hand side with the a e to the minus alpha t's all canceled out. If you do that, then what you end up with for your right-hand side is minus k over m times cosine omega t plus phi plus c alpha over m cosine omega t plus phi plus c omega over m sine omega t plus phi. Now, putting all my cosine terms together and all my sine terms together, I end up with c over m alpha minus k over m times cosine omega t plus phi plus c omega over m times sine omega t plus phi. All right? So we have our left-hand side now, and we have our right-hand side simplified out. Now what we're going to do is set our left-hand side equal to our right-hand side. And what's going to happen is that anything that multiplies the cosines on the left-hand side and anything that multiplies the cosines on the right-hand side must be equal if my guess is true. And then I have to say the same thing for the sines. Anything that multiplies the sine on the left-hand side has to equal anything that multiplies the sine on the right-hand side if my guess is true. Okay? Now I'm going to assume that I'm a good guesser. So let's give this a try. Okay? So if I look at my left-hand side and my right-hand side cosines, for my guess to be true, that means that alpha squared minus omega squared has to equal c alpha over m minus k over m. Okay? And if I look at my sine on my left and my right-hand side, if my guess is true, that means that 2 alpha omega equals c omega over m. Okay, now that sine thing, that's easy to solve first, right? Because if you look at that 2 alpha omega equals c over m omega, you get omega canceling out on both sides, and then you can solve really quick for that undetermined constant alpha. And alpha here is c over 2m. Now if you think about it, this really sort of makes sense, right? We had that alpha in our exponentially decaying function. It was e to the minus alpha t. And to me, it makes a lot of sense that how fast my decay would depend on the damping coefficient c, right? It should be some function of that. So to me, this is understandable. Makes sense, right? Alpha is equal to c over 2m. Fine. My decay constant for my exponential is proportional to my damping. Yay. All right. Now let's look at the other equation, the one for the cosine. So we had alpha squared minus omega squared equals c alpha over m minus k over m. But we know what alpha has to be if my guess is true. So why don't we go ahead and solve for what omega would be with this damping, plugging in for what we know about alpha, okay? So I want to know what my new frequency is. So in order to solve for my new frequency, I'm going to rearrange that equation and solve for omega squared. If I do that, I've got omega squared is equal to alpha squared minus c alpha over m plus k over m, okay? So simplifying a little bit more, I see that alpha squared minus c m over alpha plus omega squared is equal to, omega naught squared is equal to omega squared. Remember that k over m is equal to omega naught squared, the frequency, the resonant frequency squared for the undamped oscillator, okay? Now let's plug in for alpha, okay? Remember that we just said alpha has to be equal to c over 2m if my guess is true. So plugging in for alpha, I get omega squared is equal to c over 2m quantity squared minus c over m times c over 2m plus omega naught squared. and simplifying this bit right here, the c over 2m squared minus c over m times c over 2m, what I would get then is c squared over 4m squared minus c squared over 2m squared, right? And that gives me minus c squared over 2m squared, or 2m quantity squared, which is c squared over 4m squared. Okay, so I have omega naught squared minus c over 2m quantity squared. All right. Now, this also kind of makes sense to me. Basically, my new resonant frequency will be close to my old resonant frequency, but shifted over by some amount. How much is it shifted? Well, it depends on how much it's damped, right? It depends on the damping coefficient. So if it's a large damping coefficient, maybe it'll be shifted a lot. And if it's not a large damping coefficient, then maybe it won't be shifted much. That makes total sense to me, right? And I hope it makes sense to you. So as long as these conditions are true, then I've solved my equation, right? Yay, differential equations 1. So what we've got then would be the position with respect to time for our oscillator would be A times e to the minus ct over 2m, because remember it was minus alpha t, but we know what alpha is, and we plug in for it. We get A times e to the minus ct over 2m times the cosine of omega t plus phi. Now, your book, Kleppner and Kolenkow, your supplementary text, goes a step further in simplification and calls gamma c over m, okay? And you might remember from our previous discussions on viscous friction that tau was m over c, so gamma is related to tau. Gamma is 1 over tau. So here we have A, e to the minus gamma t over 2 times cosine omega t plus phi. Remembering that omega is described by the square root of omega naught squared minus c over 2m quantity squared, which I could now write as omega naught squared minus gamma squared over 4. All right, so that's our complete solution, okay, based on our guess and check. So you can see here that we might have, let's back up just a second, we might have a couple of regimes here, right? It depends on how omega naught and gamma, how big they are relative to one another, doesn't it? Okay, and then that would give you different regimes. So the first regime is when omega naught is greater than, or omega naught squared is greater than gamma squared over 4. If that happens, then our mental picture we had is correct, basically, right? We imagined when we guessed this solution that you displace it to the side and it oscillates, and then the amplitude of oscillation decays off. And within that envelope of that exponential decay, that you have this sinusoidal behavior. Okay, so that's what we imagined. And if you plot the function for omega naught squared being less than c over 2m quantity squared, that's indeed what you find. Okay, so for example, in a little maple plot over here to the side, I put c as 1, m as 5, k is 1, and gamma c over m solving there will give you gamma of 1/5. And then if you plug in for that and plot it for a little bit, then you can see that that's exactly the behavior that we kind of imagined in our head for what x of t would look like. Now this condition is lightly damped, and so we call it underdamped. All right, and that's the solution. Way to go, us. Okay, and then you could solve for the initial conditions. For example, if you were given some initial velocity of the system and initial position of the system and all that good stuff, you could plug in for that and determine exactly what your amplitude was and all that, depending on your initial conditions. Okay. Now there's another possibility. And that possibility is if omega naught squared is equal to c over 2m squared. Now if that happens, it's called critical damping. And it means that your frequency of oscillation is 0. If your frequency of oscillation is 0, that means it doesn't oscillate. So honestly, this means that our guess is kind of wrong, because in our head we pictured something, you know, decaying in amplitude, okay, and oscillating back and forth as it did. We didn't picture it not oscillating at all. If we had pictured it not oscillating at all, we would have made a different guess, okay? We would have not included that cosine term, right? And so I'm going to let your differential equations professor and your upper level classical mechanics professor cover the full solutions to both critical damping and overdamping, which I'll touch on very briefly. But suffice it to know for now that your guess was wrong, and so what you would have to do to fix it is a little differential equations magic, which I'll let your differential equations professor touch on. And that would shift your solution to looking like this function right here. It would look like a plus bt times e to the minus gamma t over 2. And a and b could be determined from your initial conditions, from the initial position and velocity of the problem. But you can see, and here's the important part, that there's no cosine function there. It's not oscillating, so it would just exponentially decay. Okay? And what exactly that motion would look like would depend on, did you give it an initial velocity? Did you, how far did you pull it? I mean, that kind of thing. Okay? So we would leave that alone. But suffice it to know, it's basically an exponential decay, and that's what you've got. Now there's one other possibility, and that's if omega naught squared is less than c over 2m quantity squared. Really, this would mean that you had a very kind of weak spring, and the damping is a more dominant force over that weak spring. And you can kind of picture what that would look like in your head, right? You would pull the mass to the side, and you would let it go, and the spring would try to fight the viscous friction, but it would just so slowly start to move back towards equilibrium, and you might be waiting a very long time before it even reached equilibrium again. So you can imagine that what that solution would look like is yet again a decaying exponential, but one with a much longer time constant, right? So that's what that would look like. And yet again, this means that we guessed wrong, that based upon our values of our spring constant and our damping function, that we don't see that oscillatory behavior damping out over time. So we don't have that cosine function, that sinusoidal function in there, and you're just going to have exponential decays, okay? So that's overdamped. Okay, that means that you've got way too much friction, okay, and the system is overdamped. So that's plotted out here, all three cases of underdamped, which is in the red, and critically damped, which is in the green, and then overdamped, which is in the blue. Those cases are plotted out here, and you can see what they look like, okay? All right, so I hope you enjoyed that brief introduction and that derivation of the equation for underdamping. And let me know if you have any questions, and I'll see you in class.